Okay, let's do a bit of review before I start these notes, though. Start at the very beginning. You're learning to read. Before you even get to learn to read, you learn your letters. So you need to know things like protons, neutrons, electrons, ions. You need to know how your periodic table works. Fair enough. Then you need to know how to put those ions together. You need to know how to make words. NaCl is sodium chloride. AgNO3 is? AgNO3?
Gold.
AgNO3.
Gold nitrate.
I hear it there. I've lost places. Silver nitrate is AgNO3. Hopefully at some point you're getting a little bit better at, if I say it, you know what the name is, right? Further to that, then maybe you know a few properties of AgNO3. For example, would you expect silver nitrate to be a solid, liquid, or gas? Why solid, though? Because it's ionic, yeah. Ionic things are probably solids. Now let's say I dissolved it in water. You might then be able to tell me whether it should remain solid or whether it should become aqueous. Highly soluble versus not soluble. To do that, you'd need to have the chart in your data booklet. I don't know it off the top of my head, but does that make sense? And so that brings us to where we are now. Now we want to start writing some sentences. And briefly, we've kind of started. Today's goal is to polish that up and say, well, what happens if we took NaCl, sodium chloride, and what would happen if we took AgNO3, silver nitrate? What would it do? Does that make sense? That's our goal to figure out. Tomorrow's lab, I'm going to do a whole bunch of demonstrations. And I'm going to tell you what chemicals I use, but I'm not going to write out their formulas. I'm going to tell you in words. I'm going to say, this is calcium chloride. And then I'm going to say, and this is potassium nitrate. And I'm going to react them. We're going to watch what happens. Most of them are fairly visual. And then your goal is to then write down the sentence that says, what did we start with? But also to figure out, what did we make? Does that make sense? Actually, that's a good segue into some more vocabulary. What do we call the stuff that we start with? Good, reactants, yeah. And the stuff that we finish with? Fantastic. Okay, so let's move on to writing a sentence. Could you grab the door, Julie? Okay, so my goal today is to help you practice writing some sentences. We want to remember all the little details, though. So just like if you had, I don't know, social studies with Miss Acione or Miss Mack, she wouldn't be thrilled if you started a sentence without a capital letter. She wouldn't be thrilled if you didn't have punctuation. We want to make sure we watch all those little details. So that would be like including a little 2 afterwards if it's diatomic, or a little G afterwards for a gas. Don't forget to balance. Does that make sense? So let's do an example. A very typical kind of reaction that could happen is where you take an element and you take another element and it makes a compound. Let me show you an example. Let's say I take some sulfur and some oxygen and I combine them to make sulfur dioxide. Let's try to write out an equation, a sentence that fits this. What's the symbol for sulfur? Need some punctuation here. Sulfur. State of matter? Good. Solid is right. How do I know that, though? I'm just looking at the table here because it's in black. Does that make sense? It's an element, so I need to look at the table and see what color it is. One more question I should ask. What is the allotrope of sulfur? What does sulfur come in groups of? Groups of 1s, groups of 2s, 3s, 4s? Anybody know? Sulfur comes in either groups of 1s, or I don't know that I threw it in our notes here. Let's just go back to the page on allotropes if you can find it. It's been a while. Here they are. You guys remember this slide from way back when? If you haven't written this down somewhere, write this info down. But sulfur actually comes in groups of 8. They actually call them flowers of sulfur, actually. And I think the reason why is that just like flowers have maybe 8 petals on them, sulfur also comes in groups of 8. So when I actually purchase sulfur, I purchase flowers of sulfur. So back to where we are here. Holy smokes, how many notes do we do? Okay, this sulfur requires a little 8 down here. That's like punctuation. That's very important. Oxygen. Symbol for oxygen. Allotrope for oxygen.
2.
Good. Groups of 2. Oxygen's diatomic. State of matter for oxygen. Good. Gas. Yeah, it's red. So, gas. I'll just put a plus sign in between them. So, sulfur in a group of 8 as a solid. Looks like it's going to react with oxygen in a group of 2 as a gas. And it's then going to make sulfur dioxide. That's not a compound. What kind of compound is it? Ionic or covalent? I know that for a couple of reasons. One, sulfur and oxygen are both nonmetals. I also know that there's the word di in the word. That means it must be 1 sulfur. And oxygen, we need 2 of it. One last thought. We need to pick a state of matter for this. Now, sulfur dioxide's a little bit trickier. Seeing as it's not an element, I can't just look at the table. So a few pieces of logic here. If it is an ionic compound, it's solid. It's not ionic though, so it doesn't help. So then if it's covalent, we base it on size. Little molecules are usually gases. Medium-sized molecules are usually liquids. And like big molecules are usually solids. There's 1 sulfur and 2 oxygens. It's a pretty little molecule. It's probably a gas. Now, just so you guys know, if you accidentally said liquid right here, I wouldn't actually mark it wrong. If you take a reasonable stab at something, and like you said this was an L for liquid right here, I just want you to put a state of matter afterwards. Does that make sense? Sometimes it will be wrong. Like if you put oxygen as a solid, oxygen is for sure not a solid. That makes sense? But this SO2 right here, we don't actually know for certain, but it's probably a gas. We've now written what's called the skeleton equation. However, there's a problem with our skeleton equation. Yeah, it's not balanced. We've kind of missed the balancing part. So I don't know that I'm going to rewrite it underneath. I'm just going to try to hit the balancing part up here. Here's 8 sulfur on this side. There's 1 over here. How do I fix that? Yeah, put an 8 in front of the SO4, or SO2. Good, and then Caitlin just mentioned that the 8 times 2 now means that you have 16 oxygens now. Fantastic. Let's see if this makes sense now. 8 sulfur gives 8 sulfur. Then for oxygen, 8 groups of 2 gives you 16 for oxygen. And over here, 8 groups of 2 also gives you 16. We've now written a correct sentence.
Do you have to put the water in the sulfur?
You don't. It's not a bad idea to, but you don't have to, but you could. If there isn't a number there, it's implied that it's a 1. Kind of like if I gave you a math equation and said that you had x plus y equaled 4, it kind of implies that there's a 1x. If I actually put a 2 in front of it, then it means it's 2. Okay. How was writing your first sentence? Is that something you guys could eventually work on doing yourselves? Okay. Let's try another one. You might notice, by the way, most of the notes are just examples. So let's try another one. Another type of reaction is known as a decomposition. And decomposition reactions are like the opposite of formations. Rather than taking 2 things and smooshing them together, you take one thing and you break it apart. So here's a good example. We're going to take water and bust it apart into hydrogen and oxygen. So first step, we got to write out what water's formula is. Good. H2O, not HO2. That one's wrong. H2O. State of matter for water? You know what? If you'd have said liquid, that's probably right. Is it possible that water can be in gas form? I'm sure it could. So to be honest, I mean, I just want you to write down a state of matter. But I think liquid probably makes sense. It is going to break apart into hydrogen. Well, that's H. But now, hydrogen being an element, we need to know what allotrope it has. So what does hydrogen come in groups of? Good, 2, yeah. By the way, if you don't know where to find those allotropes, find that slide in your notes from a few days back, right? And look it up. So, state of matter? Gas, because it's red. And then oxygen also comes in groups of 2, and it's also red, so it's a gas. Right, we've started writing a sentence. Now we have to balance it. You have 2 hydrogens. You have 2 hydrogens. That's good. You have 1 oxygen. That's an L for liquid, by the way. 1 oxygen and 2 oxygens. You've broken the law of conservation of mass and you've somehow made an extra oxygen. So to solve this, if you have 2 O's over here and just 1 O over here, you better double that guy. Because now you'll have 2 oxygens. But it's changed our hydrogens. Hydrogen we now have 4 of. Put a 2 there, now we have 4 of them as well. I would say this, if balancing is something that like you get, and like I just did that, and you're like, yep, got it, don't practice balancing. But if that was something where you're like, ooh, what did you just do there? I can find you worksheets. I've probably already given you worksheets where you can just practice your balancing skills. Okay. I would suggest though, don't work on stuff that you're good at. Work on stuff that you're not good at. Does that make sense? So if you know how to balance, that's fine. If you don't know how to balance, let me know. I'll work with you on it. Questions on that? Let's try another one. Wait, another kind of equation you might get asked involves what's called single replacement. Okay. And here's kind of a generic way that single replacement works. What you have is a single thing by itself, an element. In this example here, we're going to make it a metal. And an element is going to react with a compound. And what's going to happen is a changing out. This A right here and this B right here, they're going to change spots. A great analogy for this type of reaction is like a dancing in, like, say, phys ed. Right here, this is a boy, and this is a boy and a girl dancing. And what happens is they need to switch. So this boy taps this boy over here on the shoulders and says, Vamos, I'm now going to dance with the girl instead. Does that make sense? That's kind of the analogy here. Let's try an example. What's magnesium? Mg. Allotrope for magnesium. Comes in ones. It just comes in ones. Not everything actually has to come in groups of something. So most of the metals we have just come by themselves. It is a solid though. Magnesium is black, so it's solid. Now we need to write out silver nitrate. Well done. Yeah, Ag for silver, NO3 for nitrate, and they fit together 1 and 1, so we're good. State of matter? Well, don't look at the table, because the table only helps with elements. Is this ionic or covalent? Ionic. You've got a metal and non-metal. Ionic things are probably solid. Oh yeah, then we need silver. Chemical name of or symbol for silver. Perfect. Allotrope for silver? It is 1, yeah. Experience will help with this, but most metals, actually all metals that I can think of, they come in 1s. So silver is a solid by itself with 1s. And then we need to write out magnesium nitrate. Mg for magnesium. NO3 for nitrate, and good catch whoever just said that we need 2 NO3s, because Mg is a 2 plus and NO3 is a 1 minus. One of the things that I'm going to require from you guys as we further go on in chemistry, especially if you go on in Chem 20, is that you have to start being able to look at a compound name and just be able to name it right off the bat. Because you can't take 10 minutes to like go look it up in your data booklet and search and where is a, you know what I mean? It takes too long. And if I wanted you to speak a language, you can't always be like looking it up and sounding it out and going, what letter is that again? Oh, right, that's an N. Does that make sense? Like, you have to get a little bit faster at it. So, but hopefully experience makes you get a little faster as well. So, state of matter is probably solid because it's ionic. I'm just going to try to color coordinate something just to highlight how this works, literally with a highlighter. See how this magnesium right here is by itself? Now, the magnesium has a partner. You see how, where's my highlighter again here? You see how silver had a partner, and now silver is by itself? In a way, magnesium kicked silver out and said, magnesium comes to silver and says, get out of here. I'm going to join up with nitrate instead. That's why it's called single replacement. Does that make sense? You visualize that? This magnesium right here is by itself. Over here, it's got a buddy. Here, the silver has got a buddy, but then over here, it's by itself. It used to be in a tandem, and now it's not. And the other one used to be by itself, but now it has a partner. So that's what makes it single replacement. We're not quite done yet. We need to balance. And that will balance it. Again, if you're not sure how to balance, talk to me. We'll try to help. But what should happen here is you have one magnesium and one magnesium, 2 silver and 2 silver, 2 of the nitrates, and this nitrate right here, there's 2 of them. How am I doing so far? Does this make sense? Okay. Yes. Sure. Science 24. If you can even physically come over to our building, I can give you what is finished in science. Would that work? No, I'll actually give you the copy of what he's done. I saved it just in case we needed to know in the future. Yeah. So like everything that's been finished, I can give you. And that way you can figure out what hasn't. Okay. You know what? To be honest, I don't know that I can get that information right now. Sorry. Yeah, I used that. Sorry. Yeah, maybe a third. Sorry, guys. Okay. 3 examples in. Any questions? Okay, let's try another. Here's another example of single replacement. The only difference here is that now the single thing is actually going to replace the second one instead. It's still a switching of partners, but rather than, for example, a boy tapping another boy on the shoulder and saying, I'm going to dance with the girl, now it's a girl tapping a different girl on the shoulder and she says, go. Does that make sense? It's the same concept. So let's try an example. What is chlorine? Allotrope? Chlorine is diatomic. Do I not have that on that slide there?
No.
Ooh, let's double check here. If not, make sure you write that down. Chlorine is diatomic. I forgot chlorine. I'm sorry, guys. I screwed up. Chlorine is also diatomic. I'm sorry. Chlorine is another one that comes in groups of 2s. My bad. Sorry. Okay, chlorine does come in 2s. State of matter. Yeah, it's a gas. Okay, we're done writing that one out. Now we need to write out silver bromide. AgBr, and actually that fits together just perfectly. Silver's a +1, bromine's a -1. State of matter? Let's go with solid because it's ionic. Yeah. Okay, then we need a bromide, or bromine. That's Br. It also comes in 2s. What is its most likely state of matter? Yeah, bromine is actually one of the very few blue ones on the table. So it's probably liquid, yeah. L for liquid. AQ is aqueous, which means it dissolves in water. There's a difference. Okay, and then the last one is silver chloride. That's AgCl. Silver, Ag, Cl, one's a plus, one's a minus. They fit together perfect. And solid because it's ionic. This is the most likely punctuation we should use. Last step, balance it. You got 2 bromines right here, so you better put a 2 there to make the bromines a 2. And you got 2 chlorines right here, so you better put a 2 right there. And I think that does it, actually. Any questions? Okay, 2 more examples, then we're going to take a break. And then we'll finish the rest after a break. Let's talk about double replacement. Double replacement, if you like my dance analogy, would be a boy and a girl dancing, and they swap partners. So like the one boy dances with the other girl, and that boy dances with that girl. Does that make sense, the idea of like a double swap? So no one's getting kicked out and has to stand off on the side by themselves. Everyone still has a partner. We're just doing a big switcheroo, I guess. So let's try one. Lead 2 nitrate. Why is there a Roman numeral? It's multivalent. We need to know which version of lead to use. So we're using lead with a nitrate. And if there's a 2 on the lead, then we're going to need actually 2 of the nitrates. And again, it's ionic, so it's probably a solid. Sodium iodide. Again, hopefully you guys can see how I need you to be able to recognize right away, hopefully. Sodium is Na, I is for iodide, and sodium is a +1, iodide's a -1. They will fit together. So we just need a state of matter. Solid, probably. It certainly won't be a gas, I can tell you that. Okay, then we need lead 2 iodide. Good job. PbI2. Because lead is a 2, iodide's a 1, so you need 2 iodides for every 1 lead. And again, it's probably a solid because it's ionic. And then the last step, sodium nitrate, NaNO3. Also probably solid. That's an NO3, by the way. Sorry, my writing is... I feel like I'm fairly good at this board, but sometimes I'm a little blurry. Alright, last step. We got to get all that punctuation right. Just make sure it's balanced. So sometimes I just start by looking for imbalances. Like, for example, here's 2 iodides, but there's only 1 there. So let's put a big 2 in front of that. And then I might say, well, look, I just put a 2 in front of the sodium, but that sodium right there only has 1. So it probably also needs a 2. And then I'd look and say, look, well, this nitrate right here, the NO3, I have 2 of them. Hey, over here, look, the nitrate, there's actually a little 2 afterwards, so that's good. And this lead right here, there's 1 of, and that lead right there, there's 1 of. So I think we're good. If you wanted to, you could write a 1 in front. You don't have to, but you could. Sound good so far? Okay, one last example, then we're taking a bit of a break. The last example is known as a combustion reaction. Combustion reactions are actually some of the more explosive ones. When I do some of these combustion ones tomorrow, I will do them under the big fume hood because something will blow up. Kind of fun. So, hydrocarbon combustion is a little bit non-specific though. We don't know what the carbon or what the hydrogen, what the numbers are going to be afterwards. For example, it could be a C2H6, or it could be a C2. It could be a C2H5, or it could be a C3H11. We don't actually know what the numbers are going to be down here, but it'll be something that involves some carbon and hydrogen. Okay. The other part of hydrocarbon combustion is that it always involves adding oxygen, because you need oxygen for things to burn, and it always produces carbon dioxide and water. Always. So here's a very typical combustion reaction. We're going to use methane. That's the problem though. Methane is not like like a named compound. It's got one of those like formal names like water. Does anybody know what methane's formula is? Not quite. That's a different one. Anybody write them down somewhere? There was like 4 or 5 I needed you to write down. Good job. CH4 is methane. If you don't have a few of those formal common name ones written down, there was a slide, I mean, I don't remember where, but we had a slide in our notes that had about 5 of them you should know. Like, for example, water is H2O. You guys know much about methane? It is a gas, yeah. Yeah. Another reason why I know that it's a gas, though, is that CH4 is a relatively small compound. If I were to have given you C10H22, that's a lot larger because you've got 32 total pieces to it, and that's maybe a solid. Does that make sense? The gas that you put in your car is C8H18, and the gas that you put in your car is actually technically a liquid. So, anyways, moving on. Methane, gas. Oxygen, O2, also a gas. Carbon dioxide, CO2, probably also a gas, I'm guessing. And good old water, H2O. You know what, 9 times out of 10, if you put liquid, I'd probably say you're right. But when you blow something up, usually it gets hot and it vaporizes the water. Most combustion reactions, actually we learned a word 2 days ago. A reaction that gives off heat is called? Nice, good job guys, exothermic, yeah. So most combustion reactions give off a lot of heat, so much so that it vaporizes the water. So it should actually be water in the gas form, not the liquid form. Another reason why, if it actually produced water in the liquid form, water would probably put out the fire, and that's not what happens when you blow things up. So, okay, last step, let's balance this thing. My hope is that you're getting a little bit faster at being able to look at it and just see, okay, look, put a number here and here. But like I said, if you're struggling, we'll do practice. Carbon and carbon, they're good. You got 4 hydrogens here, but this guy's only got 2. So let's put a 2 in front. There's 4 hydrogens here, and now 2 times 2 gives you 4. Yeah. The only thing left is oxygen. Just make sure you're careful, though. You have oxygen in more than one place. Here's 2 oxygens, and there's 2 more. So you have 4. What number do you have to put here to make it so you get 4? Good job, 2. Now we're done. Okay, one last thought, then we're taking a break here. If you can do that, that's great. It's fantastic. But we kind of cheated a little bit because I told you everything in the equation. I told you the 2 things we started with, and I told you the 2 things that we finished with. In real life, it may look more like this. I'm going to tell you what we start with, and it's your goal then to figure out what will it make. And so that's our last challenge for the day, is we got to do a very similar concept, only we actually have to make a prediction as to, well, what will happen. That's what good scientists can do. They can not just make a hypothesis, but they should be able to say, no, I know that if I combine this and this, I know what it's going to make. Does that make sense? So go take a 5-minute break. When you come back, this is our last goal. Okay, so here's our goal then, one more time. A good scientist doesn't just mix 2 chemicals together and go, boy, I hope I don't blow up. A good scientist actually knows what's going to happen before he does it, or she does it. And that's my goal here, is to give you the start of a sentence and say, you finish it. And that's what we're going to do in tomorrow's lab. In tomorrow's lab, I'm going to tell you what chemical A is. I'm going to tell you what chemical B is. We're going to react them. And I will not tell you what it makes. It's going to be your job to figure out what it made. Does that make sense? That's our last challenge. So, in order to do that, my suggestion is you need to figure out what type of reaction is going to occur. There were 5 types. Formation involves 2 things coming together. Decomposition, one thing breaking apart. Single replacement is like a 1-for-1 swap. Double replacement is like a 2-for-2 swap. And then combustion is kind of a weird one on its own. So the first thing I'd recommend is let's look at the start thing here and figure out what is the most likely chemical reaction to take place if we only start with one thing. Decomposition, yeah, it's the only really possibility. Hey guys, can I make sure everyone's like focused? Thanks. This should be decomposition because we've only got one thing to start with. So we need to take lead and bromine and break them into pieces. So that'll be lead by itself and bromine by itself. Now let's get the details right. What does lead come in groups of? Ones, yeah. Don't even bother writing the one. It's probably a solid then. What does bromine come in groups of? 2s, and bromine is probably a liquid. Last step, balance it. Lead's actually good. You got 4 bromines to 2 bromines, put a 2 there, we're done. And this is what you guys are going to do tomorrow. I will only give you the start. The new challenge now is figure out, well, what's it going to do? So let's try another one. This next one, do we have 2 things that are elements combining together? Technically not, these aren't elements, these are 2 compounds coming together. And since they're both compounds, we have to do like a double switch, if that makes sense. So we need this nickel right here to go with that guy right there. And we're going to want this sodium right here to go with that nitrate. You guys see how like I color coordinated them so they flip? I don't actually care which one goes first. We just need to make sure we write both of them. So why don't I do nickel with SO3? NiSO3. Hang on a sec. Nickel. It has more than one charge. We have a periodic table nearby. What are the charges for nickel? 3 plus and 2 plus. Okay, so here's the issue then. Your periodic table tells you which one is most common by letting you know the first one is most common. Okay, but we can actually tell you which version of nickel we were using by looking at this compound right here. Nitrate is a -1, and we used 3 of them. It means we must have been using the +3 nickel. When using equations like this, if you start with a +3 nickel, we're always using a +3 nickel. So even though +2 nickel might be more common, if this one started with the +3 nickel, this one here better also be the +3 nickel. What's SO3? It's called a sulfite if you have a periodic table that's not blurry. And it has a charge of -2. So to make this compound properly, you better use 3 of those. No. You better use 2 of those and 3 of those guys. And I'm just going to erase those charges because we don't really need them there anymore. One more step. It's probably a solid because it's, I don't even know I didn't write solid there. Because it's ionic. Are we done? We haven't actually flipped both partners. We haven't accounted for the fact that the sodium needs to go with the nitrate. What's the charge of sodium? +1. Nitrate's -1. They fit together perfectly. Just add a solid afterwards and we're good. Last step, we got to balance this thing. I'll use green for balancing. Okay, let's give it a try. Look for something that's not balanced. Like say here's 2 sodiums. And there's only 1 sodium right there. So let's put a 2 there. Here I have 2 nitrates. 2 of the NO3s. Over there I have 3 of them. 2 and 3 don't really fit very well together, do they? So 2 and 3, they multiply to give 6. Let's try to get 6 of each. So here I have 3. Let's put a 2 in front. That'll give 6 of them. And I have to change this number over here. Let's make that a 6. So then now I have 2 times 3 for 6 nitrates. And over here I have 6 nitrates. You know what else that helped? See this little nickel with a little 2 afterwards? Well, now look, my nickel has a 2 in front of it, so that helps. This SO3 right here has 3 afterwards. This SO3 right here actually only has 1 of them. So let's put a 3 in front. Oh, that's not a 3. It's like a 3 with an extra hump. There we go. Okay, let's see whether we've got it fixed. 2 nickels. Nickel with a 2. That works. 2 times 3 gives 6 of the nitrates. And this 6 right here is for the nitrates. 3 times the little 2 gives 6 sodiums. And look, 6 for sodium fits. And then 3 of the SO3s. And here's an SO3 with a 3 afterwards. We're good. How am I doing? Are you able to follow that? This is really the culmination of a lot of skills. You need to know all your chemicals. You need to be able to write the formulas properly. You need to be able to balance them. Right? Like what we're doing here is really like reading. You need to know your letters. You need to be able to put them together in words. You need to be able to do all the little details right, because there's a lot that you have to do to get one of these questions correct. Okay. In the interest of... No, I should do the last 3 here at least. Zinc, I didn't actually give you a formula for zinc. What would zinc's equation formula thing be? Zn, and it's probably going to be a solid. What about sulfur? How many?
8.
8. Good memory.
8.
Alright. Any ideas what kind of reaction this will be? You've got an element and another element. Yeah, we're going to form something and shove those 2 elements together. So we got to figure out how zinc and sulfur go together. Are you looking for the key? What's the charge on zinc? 2 plus. Charge on sulfur is minus 2. Actually, they fit. It's probably solid though. Last step, let's balance this thing. Zinc and zinc are good. But here there's 8 sulfurs. And this guy only has 1 sulfur. So put an 8 in front. Except now zinc is not balanced. Put an 8 in front of zinc. Ta-da! For the test, yeah, there's one up to the front somewhere in the file. Like on the clipboard. Two more. Copper. What's copper going to be? Copper. And it's a solid. It doesn't need a group of 2 or anything. Au is gold. What's a chlorate? Not S. ClO3. Close. ClO3.
Because he's hot.
Alright. I need to figure out the charges though. Gold is a 3 charge. That's a 3 up there. And chlorate's actually minus 1. Maybe I'll try to bring that a little higher up so it's not so high, so low for you guys. Do they fit together? Sadly they don't. So you need to put a big 3 around the chlorate. And then it's probably solid. Because it's ionic. Okay, our next challenge then. Now that we've actually written out the start of stuff, we got to figure out what's it going to do. So our choices are formation. 2 elements coming together. That's not what I have. Decomposition. 1 thing breaking apart. Also not what I have. Single replacement. An element and a compound where we do like a single trade-off. That's what we have here. Who trades with who, though? Gold and copper will now change places. This is like this boy right here taps this boy on the shoulder and says, I'm dancing with chlorate. She's really pretty. Chlorate's pretty. I don't know. All right, so copper and chlorate need to go together. Here's the problem, though. Copper has more than one charge. Now, previously when we had this problem, I went back and I looked at the previous example of copper and looked for its charge, but back here copper didn't have a charge. So in this example here, we'll just have to go with what's most common. So is the 2 plus more common or the 1 plus more common for copper? Which one's first?
1 plus.
2 plus.
2 plus. 5 plus.
It's 2 plus.
8 plus.
Okay, it's 2 is first? Okay, 2 is first apparently. So that means we better put a 2 around the ClO2 then. ClO3. And it means that gold will be by itself. Gold gets kicked out. That's the boy that's got to go stand on the sidelines. And I've also been a little lazy. I should include states of matter, so probably solid and probably solid. I'm just going to erase those little charges up here because we don't need them anymore. Last step, let's balance this thing.
Does that say S or G?
Sorry, that's an S back there. Gold is probably a solid.
Yeah.
It's a metal. It's black. Okay, last step then, balance. You know what? Everything is balanced on this thing except for that chlorate. Here there's 3 and there's 2. And 3 and 2, the only way to make them fit is to make 6 total. So put a 2 here so that there's 6. And put a 3 here. That makes sense? And then you'll probably need 3 of these guys and 2 of those guys. Now our census is complete. Okay, let's do one last example, and I'm going to let you guys try some. Because sometimes the best way of doing it is you kind of just have to try it yourself. I can show you, but at some point you got to be like, okay, I'm brave, I want to do it myself. But before that, let's do one more. What kind of reaction is this last one? It's combustion, actually. C6H14, it looks like it might be a single flip, but do you see how this guy, they're both nonmetals? So it's actually slightly different. Combustion always does the same thing. You have a certain amount of carbons, a certain amount of hydrogens, and I don't know how many there are. It always adds to oxygen, and it makes the same 2 things always. Carbon dioxide and water. Always. Just throw those states of matter back in. This guy was a liquid because it's kind of a medium-sized molecule. This guy's a gas. That's a gas. And there's a really good shot that water, if you blow something up, water will be in the form of vapor. So, all we got to do is balance. All right, where do we start? 6 right here for carbon. This carbon only has 1. What's 6 in front? No, there's 6 on both sides. Any ideas what to try next? Oh, hydrogen, sure, it's next. Thank you for saying hydrogen, whoever did. Okay, how many hydrogens? We got 14, but there's only 2 over there.
7.
Good, yeah, 7. We need 7 times the hydrogen. There we go. Perfect. Be really careful now with oxygen. All right, you got 6 times 2. Okay, 12. And you got 7, and I guess there's a 1 there, so you got... Well, no, the 2 just applies to the hydrogen, and I was talking about the oxygen. So, like, you have 7 times 1, I guess. You have 7. How many total oxygens do you have then? This is a problem. Because you can't take 19 and somehow use groups of 2 to get to 19. Well, you can. You use a decimal number. So you say like what's 19 divided by 2? And 9.5. So in a way, you could probably put 9.5 right here. Because 9.5 times 2 is 19.
Double everything.
Yes, good. Okay. Now, before we talked about, like, that's what you do. But there's a reason why we double everything.
So it's not a point back.
You can't have half a molecule. Does that make sense? Like, oxygen is, as a compound, it's a small unit of matter. We really can't cut it in half. So it's better, more appropriate to double everything. So make this 1 into a 2. 9.5 doubled would be 19. We just said that a minute ago. 6 getting doubled. Good. And 7 getting doubled. Perfect. You know what? It probably doesn't hurt just to check our math one last time. We did all this work. We may as well check it again. So from the top. 2 groups of 6. That's 12. 12 carbons. 12 carbons. Good start. 2 groups of 14. It's 28. 2 groups of 14 is the same, though, as 14 groups of 2. So that one's good. 19 groups of 2 now. 19 times 2. Good. Yeah, it's 38. Just write that down there. Oh, wait, over here we have oxygen coming from 2 different locations, so we'll have to put them together. 12 groups of 2 is going to give us, right up there, 24. 12 times the 2 is 24. And then 14 right here times by, I guess, just 1 oxygen, so 14. 24 and 14 equals 38. We did it. Did I lose you there? You're good? Okay. Okay, I've shown you a ton of examples now. I don't want to say that's the easy part, but watching me do it is completely different now from try it yourself. So we've got about half an hour left. My goal for the next 2 days is to help you guys practice writing your own sentences. So on this slide right here, I want you guys to give it a try. See whether you can figure out what it'll produce. And then tomorrow for our lab, I'm going to do about 10 demonstrations. I will tell you what I'm combining, and it's going to be your job to figure out what it made. Fair enough? Okay, take some time. Try these examples then. Call me over when you think you have something. I'll try to help out.